The last video started by talking about IMFs in general and then focused in on how, for different types of substances, the different attractions would hold them in a solid state. But it's important to understand how IMFs apply to all states. So when we have a molecular solid, it is in the solid state because the intermolecular forces are strong enough to hold the molecules closely together. So here we would have a solid. It has a definite shape and a definite volume because the molecules do not move around. The particles vibrate in place rather than going from one place to another because the attractions are strong enough. That could be in ionic, metallic, or network solids, a bond, or in a molecular solid, the IMF being strong enough. If they have a regular, specific 3D pattern, it would be crystalline. That occurs for sure in ionic, in network, and in metallic. But some molecular could be crystalline, while others are amorphous. They don't necessarily have the same orderly arrangement. When we put enough energy into a solid, it causes the particles to move a little bit faster. The particles in a liquid are still in close contact with one another, meaning the IMF attractions are strong enough to hold them together, but they're not strong enough to hold it in place. For certain substances, metals, for example, it has to be hot enough and way above room temperature for that to happen. For many molecular things, it isn't quite as hot because the IMFs are weaker. All the particles are moving faster. The arrangement of them is much more free, and depending how strong those IMFs are, depending what types of IMFs they are, may determine the properties or change different things, may change the surface tension, would change the viscosity, how easily they flow based upon how much they stick together. But in all liquids, we still have that defined volume. Solids and liquids have defined volumes based upon how closely packed the particles are. But the shape can change when we go to the liquid state. Gases are unique and significantly different from the other states because they can take the shape and volume of their container and because the particles are so far apart. We talk about or model it as if the IMFs don't exist or insignificant, which is why it's important to note that most of the time to boil something takes much more energy than to melt it. Not only is it a higher temperature, but the energy change itself requires more energy because rather than slightly separating the molecules and allowing them to move freely, we are getting them to move much more freely and they are much farther away from one another. The exact arrangement or the spacing of the particles depends on temperature, volume, and pressure, which we'll explore more about the property of gases here. But those attractions we mostly ignore or we treat as if they aren't happening in the gaseous state. So all of these, or which state we're going to be in at room temperature or any given temperature, is based upon the IMFs. And then we can see the different effect of those IMFs based upon the state.